There's a very full classroom of 2 out of 20 students here, or however many are supposed to be in here. But that's here. We haven't met for about a week. It's been at least, well, it's been a week and a half since we met, and we won't meet again for another week and a half. So these meetings are getting kind of far in between. It's almost as bad as last April when I had this, stroke last semester. We've had about 2 weeks without meetings at there. But let me just kind of review a few things on actuators. After the semester break, I will kind of wrap up robotics, and there will be a midterm online test that you'll have to take on robotics. That's there, and that'll be online, and a good portion of that will fall on the final exam. So that's an important that's there. So let me slideshow from the beginning. This is only like 25 slides. Let me go through them. Right, there's display settings. Let's duplicate that there. Okay, so both slides have the same thing. Okay, an actuator, is a major part of any robotic system. We've already talked about the arms and the various other parts. I'm not going to review those, but the actuator is one of the things that will show up on the final exam in this set of slides, which I'll post later on VLE. Come on in. Oh, looking for the wrong class. That's there. Yeah, as I said, I didn't have a pin to write on the board, so hopefully if anyone else comes, they were late and they missed us. But actuators are what actually moves the arm, right there. And typically they have multiple parts right here. A power supply, a power amplifier, servo motor, transmission system. These are all various parts. I didn't bring the motors, some of the motors with me. I meant to bring them, but that's there. You'll see them on the robot anyway. You've already seen them. But again, typically when we look at the actuator system, we have a source of power. Now, this source of power can be one of 3 types typically, although there are more. Electric, pressurized fluid is in terms of hydraulic fluid, although water can be used as a actuation. Or compressed air. Now, the robots we're using in this class use electric right there. We have the input control power, usually electric. That's actually the information that comes from the computer, the microcontroller that's there. So we have some power losses. I'm not going to get too wrapped up with that there. This particular set of slides goes into more detail that there. These all here, and I forgot, my pen doesn't like this right here. Yeah, I'll just use this right here. These 3 all refer to power losses when we look at the efficiency. I'm not terribly worried about the efficiency for this discussion. Our power amplifier then goes to our motor or servo motor. Now, this motor may or may not be electric, right there. So this power amplifier may actually open a valve right there. And then this goes into our transmission that actually drives the arm or the end actuator itself right there. So this is a typical block diagram. Some characteristics that we have to deal with is what is our load. Obviously, you need a different type of motor if your goal is to pick up a tire on an assembly line than to pick up a small piece of an IC in order to make silicon chips. If you're at Intel and you're making microprocessors, your actuator can be very small because you're talking something that weighs way less than 50 grams. But if you're putting tires on a car at Proton, you're looking at something that weighs 10, 15 kilograms right there. Speed, fast enough, but not too fast. Obviously, if you're in manufacturing, you want this thing to move as quick as possible, but not so fast that you can't control it. Accuracy. Accuracy is how, and accuracy is different than resolution. That's there. Repeatability, accuracy, and resolution, all three come together. Accuracy is how close you get to what you want. Resolution is how tightly you can control it. So if you're trying to put together an automobile, plus or minus, 0.1, millimeter might be accurate enough for placing a door. That's there. If you're placing on an integrated circuit and you're placing the electrical bond wires, 0.1 millimeter is way too, too far apart. And that's where the resolution is how accurate does it need to be. And the repeatability is how well you do it. The old, you've got a target right here. Here's a target. Here's the bullseye. Accuracy means that I can get into the bullseye right there. Repeatability means that I can do it every time. Now, I can be very accurate, but be hitting all around the bullseye, but I never hit the bullseye itself. My resolution is poor right there. I'm very accurate and I'm very repeatable. But if I got a grouping over here, it's very repeatable, but my accuracy's off. Right there. I hate to use going back to the old weapons technology, but that's there, or even GPSs. I'll use a GPS. A GPS is a global positioning satellite system that has 3 satellites that will look down, and these are up in space, these satellites, and your car here sends a signal out, and it gets a direction from here, gets a direction from here, and it gets a direction from here. And it triangulates between those 3 satellites, more the better, that what your position is. Now, these satellites are owned by, the U.S. military. The United States military owns the satellites that GPS is based on. They're not put up there by some international UN committee. They were put up there for one goal, and that one goal only was military purposes. They've opened them up. When they initially opened them up, they deliberately put in a plus minus 50 meters so that when you try to get your position on a map, you'll be here, then 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 you'll be here. These are all within 50 meters of each other, but it's not, the resolution is plus minus 50 meters. And that was deliberately done because they didn't want other countries to use these satellites for military purposes. They maintained the technology to remove that 50 meter and get down plus or minus 0.5 meter. But for civilian use, it was plus or minus 50 meters. And if you get back to where the GPS came, why it was opened up, was there was a South Korean flight supposed to go to the U.S. It's off course, flew over the Soviet Union, Russia, and flew over the Soviet Union because there was an error in their navigation system. GPS was not open to civilian use at that time, and Russia shot it down. This was back in the 1980s, right there. After that, they opened up GPS for civilian use. But when they did that, they deliberately put in an error of plus or minus 50 meters, right there. Well, that's where this resolution comes in, right there. And again, I can't write my lines because this pen and this projector doesn't seem to agree with each other. Right there. So repeatability is it going to work the same every time? One of the things you'll find when you do this lab that I'm going to talk about after I get through most of these slides is that these particular servo motors aren't very repeatable. They lack feedback right there. Reliability, mean time between failures, how often does your robot fail, and our power consumption, how do we feed it, that there, how big a power supply we need right there. So, types of actuators, you will be asked on the final exam and the midterm, name the various types of actuators and what they are. So this slide is one you'll probably want to submit to memory right there. So pneumatic air, they utilize pneumatic energy provided by a compressor. It performs as mechanical. This is very, very common in very small robotic type systems. If you go to Intel, or well, I was going to say Altera, but Altera is not on my Intel, or Freescale, or any of the IC manufacturers, Texas Instruments, you'll find that a lot of their actuators are pneumatic. That's there. And again, the reason is because one is if you're dealing with ICs, the last thing you want is any kind of electricity around there. Static electricity causes problems. That's there. And you don't need much energy. IC integrated circuits or chips are very, very light. That's there. So you don't need a lot of power. That's there. So they tend to be fairly small. That's there. Hydraulic, these use a type of fluid or oil. You'll find these in a lot of very high energy, power type things. In an automobile plant, they use a lot of the hydraulic actuators. That's there. If you look at it, it's not as common here. I don't see the car lifts, where you pull into your car and they have a giant lift that lifts it up. That's there. No. That's there. Normally, you'll see somebody that uses the little the little pump. And by the way, that little car pump that you use to pump jack up your car, that's a form of a pneumatic actuator. So air can be used to carry a lot of weight. It's just that you have to compress it fairly heavily. But there are hydraulic actuators that and they're used usually hydraulics have the problem, and actually pneumatics do, but pneumatics is not a problem because it's big a problem, is that any leak will give you a nice slippery spot on the factory floor. Back in my younger days, when I was about your age, maybe younger, I worked at a company that made brake shoes and clutch facings and that's there. And we had a lot of hydraulic power in the factory. And these hydraulic pumps would pump this oil up to, that there was a red oil. It looked like what you put in the transmission in your car if you've got an automatic transmission, or the power steering pump. Again, a power steering pump is a hydraulic actuator. So if you look at your car and you look at your power steering pump, that's hydraulic. That there uses an oil right there. Now it's different than the oil you put in your engine, although you can almost use the two of them interchangeably. I don't recommend it because the seals are not designed to handle that there. And they have different detergents they have different viscosities. But the hydraulic fluid inside of a power steering pump is sometimes almost the same as what's put in the transmission. The transmission is being used as an oil for lubrication. In the power steering pump, it's used as an actuator to drive the power steering motor right there. So when you look at oil used, they have two different purposes, so they're a little bit different. But transmission fluid and power steering fluid are actually very similar to each other. And then most actuators out there are electric. Electric kind of bridge that area between and they're actually easier to control right there. So, I'll talk a little bit toward the end, and I'm not sure. I said I was going to only talk 20 minutes, but I'll probably end up talking a little longer. But they're pneumatic and hydraulics are powered by moving fluid, and I'm just going to they both fall under the category, and you need to know this as well, of linear actuators and motors, the difference between that. That's it. And by the way, I only have like a week or two of robotics, and we're going to switch over to industrial automation, where we'll talk about PLCs. Right? So here's a linear actuator. That there you have a piston, a fluid port there that we will push fluid here to push the piston out this way. This is similar to the way that the bracket pinion would work on your power steering, the way that's there. And again, they both work on the same principle. Air is a fluid. Water is a fluid, oil is a fluid. They all work on the same principle, right there. So simplest would be to actuate a linear joint by a moving piston. I'll skip all these formulas. You don't have to know the formulas right there. This gets into the rotating, where we've got a vane that we push fluid in, and that's there, and it comes out the other side, and this rotates it. That's there. Again, this is a type of rotating motor that uses a oil or air as the actuator. Again, it's the same thing. Sure. So we've got this shaft that rotates left or right, depending which direction we push the fluid into. Right there, and we got, again, I'm not going to go into the formulas. These are pneumatic. Again, this slide is one of the slides that you probably want to look at, because I'll ask the advantages and disadvantages of various types of actuators. And it's all covered in this slide up there. And then the same thing for the hydraulic up there. Again, high efficiency, high power to size, limitation right there. There's a risk of fire. What I was going to say, and I got sidetracked about the brake shoe factory, we would every now and then run into a problem where a hydraulic fluid or hose would break or start leaking. We would end up with a huge pile of oil on the floor. Or worse, somebody would get sprayed with high temperature oil and be injured. We've never had any serious injuries, although one guy got it in his eyes, and we got him under the eye wash fairly quickly. He didn't lose that. Right there. Changes in temperature. This is not a problem in Malaysia, but it is a problem where I was working at the time in Indiana, where we didn't necessarily heat our plant very well. We had some machines that were around the windows, and it gets to minus 15, minus 20 degrees inside that plant. And we're talking Fahrenheit, so you're talking considerably colder Celsius. Although, minus 20 is probably, minus 40 they're the same. It didn't get to minus 40 very often, but you would see Celsius, you'd see minus 30 fairly regularly out there. So if the fluid got to minus 30 or even zero, it would get really thick and sluggish and slow the motors down. That was a problem. That's there. Both the hydraulic and the pneumatics actually have the problem that they're, so they don't mention the noise. The noise, sometimes you'll hear that every time you use that there. The hydraulics, it's pretty noisy at times right there. So, electric, there's basically three types of electric motors right there. There's the standard DC motors that they don't talk about much here, the servo motors and the stepper motors right there. But they're electrical mechanical devices. You take lots of courses in motors. I'm not going to go through a great deal of those right there. But they're, again, they can be used for everything. I mean, you'll find motors in everything. My car back in the U.S. had a little electric control on the seat. I could move it forward, backwards. also my Peridua is not quite as nice. I have to move the seat. My mirrors I can adjust. Everything in my car. I don't have a sunroof up there. Sunroofs are a pain in the neck. Don't buy cars with sunroofs. But they're, the blower motors and the engine cooling fans are different than the seat adjustments and the power windows and the mirror adjustments, because those just spin and we don't care about how fast they spin as a general rule. We don't care about position. But obviously, adjusting your mirror to where you can see the cars behind you electrically, you need to be able to control the position of that door. Same thing with medical equipment, x-ray equipment. I had the pleasure, and I use the term loosely, of getting an MRI back in April. And MRIs use a lot of motors that rotate around and take pictures of my brain. They actually found a brain there, but they also found little spots where I killed it. But some of this equipment has to be very precise and very, very, medical equipment. So, and especially with robotic surgery being done. I'm going to skip that. You've already seen this slide, right? If not, you should see this slide. That's basically how a motor or generator works. You have a rotating armature inside a magnetic field right there that will either, if we apply mechanical force and rotate it, it's a generator. If we apply electrical force, then it will rotate on its own. It's a motor right there. And this is a DC motor with brushes right here. This is a very basic DC motor right there. Components, again, I'm not going to go through these slides. We've got 3 types of motors they talk about here. A DC motor just simply rotates right there, and we can control the speed of the motor various ways. The most common way is by varying the DC voltage to it. That's there. However, if we're doing microcontroller process, that's there. We use something called pulse width modulation, which I'll talk about after the break. AC motors are a little harder to control the speed. Normally, you do use what they call a synchronous motor, and will control the frequency. That's there. And then a servo motor can be DC, AC, or even some motor when we have feedback. Now, the motors that we're using are servo motors, but we're not using any feedback. That's it. So we'll talk about those motors here. Components of a DC motor, right there. Let's just get us into it. Stepper motor are very commonly used. They've been around for a long time, and we control how far the motor moves by a number of steps, pulses. We send pulses to it. That's there. And here we have how many resolution steps per revolution. The first one gives you 4, then you've got, looks like 8, and a much higher number. And you can actually get a step that's there. But again, we're looking at the step angle, the number of steps that there, and these are the number of poles. So we have various, and we can energize these 2. Then we energize these 2, that causes a turn. Where we energize, and you can see they're showing that we're rotating around and we're actuating various ones right there. This is kind of a neat little slide. Again, I'll post the slides up on BLE. With the stepper motor, we're not using stepper motors with our labs, but I've used stepper motors in the past for various projects right there, and they're a really neat way of controlling. My old satellite dish I used to have in my house used a stepper motor to control the position of the satellite dish, where it looked at, the dish would point to different satellites in the sky, and I would pick up different television stations, and it was on a pivoting arm, actually, right there, that would just simply rotate it, and I would tell it that I wanted to set it to say 68 degrees, and it would point to a satellite that's 68 degrees off the horizon, or 90 degrees, which would point straight up ahead, or 120 degrees. And all the satellites were on an arc. Here's your house, and all the satellites were on this arc, and you would point to different satellites right there. And you would just rotate the dish to point to different satellites right there. And one of the problems with it was it didn't have any feedback, so every now and then it would get off because of slippage or wind would blow or whatever. Because I mean, this was a 10-foot dish sitting on top of my garage on a large pole. Yeah, I don't think they're legal here in Malaysia. I don't think individuals can own satellite dishes, but you've seen what I'm talking about out there. But it allowed me, and there was different satellites. You know, there would be a satellite here, a satellite here, a satellite here, a satellite here, a satellite here. Each satellite would had at that time, this was 25 years ago, 20 years ago when I had this dish, that their cable TVs kind of removed the need for satellite dishes right there. But each satellite dish would have 24 transponders, which would be a TV station. So if I wanted to watch my favorite football game out of Minnesota, which is why I had the dish, so as I can watch American football, I would point to this satellite. If I wanted to watch some TV station out of Canada, I would point to this dish right there. But the problem you run into, because there's no feedback, I would have to calibrate it once in a while. Fortunately, my receiver had a calibration function where it moved it to one step, one direction. That was 0 degrees. It moved it totally the opposite to the other direction, 180 degrees, and it would recalibrate the processor to where it knew exactly where it was at, right there. Again, this is the advantages of electric, and this is, they group all the electrical together in the slide. We have wide variety of power supplies. Basic drive unit is usually lighter than fluid. They are more, they are more efficient. They don't have any pollution. You don't have to worry about oil getting on the floor. They are typically more repeatable and accurate than fluid or pneumatics. Both the hydraulics and pneumatics have to be calibrated. And there are some limitations in terms of power, right there. The transmission system can be tricky, and they can't be used in some environments. I mean, if you're dealing with, for example, the handling of gasoline you probably shouldn't use electric, because electric tends to have sparks when the motors move internally. So it's supposed to be environment. Again, this slide, along with that other 2 slides, you'll need to know right there. Applications right there, and they give an example. Again, when we look at, this is for steppers, printers, the old printers, now the laser printers don't use servos, stepper motors right there. But the old dot matrix printers did a lot. Plotters will use medical equipment fax. So that's there. Again, this is actually a fairly good slide right there. Again, I'll probably steal parts of it when I write the final exam. Right. Hydraulic, again, we get into all the various comparisons right there. So we've got 2 slides that actually go through, and that's it for the slides. Now I'm going to just talk a little bit about the lab right there. I'll come back. I posted the lab. You already did the first part of the lab. And the first part of the lab is that there is a, I give you a little file and I go through step by step how to talk to the motor. We did this before, I did this in class, but now it's been 3 weeks, so I've really forgotten it, right? So I put it at there. And we'll meet next Monday in the lab. Hopefully everyone else will get there, and you'll start working on this right here. And this kind of goes through so this is part one, is just playing with the lab. Just that you already did part one, but you'll probably have to repeat it. Part two is I just basically want you to pick a spot, write the code to pick it up, move it 5 times, and then see how repeatable it is and how accurate it is. In other words, you pick up, I think last time I said something like a small, I use the concept of like a chess piece or something like that. Would be that they're a small bottle, for example, like the ladies would buy for their nail finger polish, although that's their perfume bottle or something like that. It's got to be something small enough and light enough that you can pick it up right there. And so what you'll do is you'll write a lab report. Now, you could do this in groups of up to 3. In other words, there's enough robots where 3 people can grab a robot and do the lab. Each person needs to submit an individual report through VLE along with a video. And then they have to be 2 minutes. Your video only has to show 1 iteration, because uploading the video to the VLE, it can't be very big. So pick the lowest resolution you can on your phone and keep it short. Just one motion, just to demonstrate that thing. So again, there. And again, this basically says it's a standard report with introduction, lab objective. What is the objective of the lab? What equipment, what robot number you use, and there's a number on the robot, say what number it is, what version of MATLAB, the steps you did. The data basically is just kind of a short little description of this time. First time it landed here, next time it was so many centimeters away, the next time it was so many centimeters away. That's there. So there should be 5 readings. The first one will be 0 because that's your initial move. And then after that, you'll have 4 other moves, and you'll say how close you were to the first one right there. And then, which again is part of the data. That's there. The data should, that's there. Your drawing, just a basic hand drawing. And then your MATLAB code in a video, right there. And if video is small enough, you can include it in the Word document. Otherwise, you have to. Right there. And then your conclusion. That's there. And each student's expected to write that there, Andy. And do not allow your lab partner to submit 1 report and then come back to me later and tell me that you got a 0 for the lab because you didn't submit a report, but my lab partner did. That's not acceptable. Each student must submit a separate lab report. That's there. And this last line should make that clear. So, with that said, I am going to, I said 20 minutes. I talked for 33 since I started recording.